And we are live.
Hello, everyone. Welcome to Universe at Home. We're just going to take a couple of minutes here to let people join into the YouTube audience and kind of like settle in, make sure everyone's getting updated on the stream. So for these first 5 minutes, if you're seeing us live, then, feel free to kind of just kick back, check your phone. Not that you're not allowed to later on or anything like that. Yeah, we're just going to take a handful of minutes here. And once it's about 8:05 on our end, we'll get started with the actual presentation, all right? All right, I'm just going to update here again really quick in case you've joined since the previous announcement. We are just waiting for everyone to kind of like settle in and load into the YouTube, make sure that it's all sitting ready to go. So we're just going to take a couple more minutes here just to make sure everyone's connected and settled in. All right, so once again, we are just taking a couple of minutes here, making sure that everyone is able to connect to the live stream, get settled in, and have an updated connection. So again, on our end, once it's about 8:05, we'll get started with the presentation. Thanks for your patience, and we'll be going here in a little bit. All right, everyone, we're going to get started here in just about a minute. We're just still letting the live stream settle in and take off, okay? All right, so we're going to get started now. Hello, everyone, and welcome again to Universe at Home. My name is Corbin Condon. I'm a senior in astrophysics here at the University of Minnesota, and tonight I'll be your main presenter. I'll briefly let my colleagues introduce themselves as well. Ethan?
Hi there, my name's Ethan Rovstotz. I'm a senior in physics and astrophysics at the U of N, and I'm going to be your activity coordinator for the night.
And Daniel?
Hi, everyone. I'm Daniel. I am also a senior in physics and astrophysics, and I will be the moderator of this stream, and I will record your questions, and we will answer them during the Q&A sections.
All right, so tonight we're going to talk about things that go bump in the day, the state and processes of our sun. As a quick apologetic note, my personal Wi-Fi has been acting up today. In the case that I disconnect for whatever reason on my end, Daniel and Ethan will take a short break to answer some questions while I reconnect. We're also going to talk about each of our three topics separately, and we'll take a quick break for questions after each of them. So, to begin, I'd like to introduce our topic, the sun. If by some chance you're unfamiliar, the sun is the thing in the sky that if you look at it, it hurts your eyes. Big ol' hot boy in the sky. Throughout public school, it's likely that you've heard such things about how maybe the sun is a star, how it fuses atoms, or maybe that it's relatively small for what it is. So tonight, I'll be telling you about some things that you've likely not heard before about the sun. First, we're going to talk about the true color of the sun, what implications that has for us here on Earth, and why it might not match up exactly to what that color looks like for us. Next, we're going to talk about things that happen on the surface of the sun, or rather, we'll use the term photosphere. We'll define that later on. We'll talk about solar storms, things like coronal mass ejections and solar flares. And lastly, we'll talk about the life cycle of our sun, including how it formed, what makes it a star right now, and what it will go on to do. Again, after each of these topics, we're going to take a short break to answer questions. And after the discussion on solar storms, Ethan is actually going to lead a short, scientifically relevant activity. However, without further ado, you and I have a hot ball of plasma to discuss. So, regrettably, to begin talking about the color of the sun, I need to jump through a couple of hoops first. We're going to talk about one thing specifically right away: electromagnetic radiation, or you can call them electromagnetic waves. This first slide I'm going to put up after this one of some nice composites of the sun is going to be the most crowded. And for that, I'm sorry, but I think that you and I can talk through it. So, electromagnetic waves are a type of energy that gets carried across spaces, and in this case, across space. Now, you can consider electromagnetic radiation, or waves, to be a stream of tiny particles called photons. I'm going to use this word later on in the presentation. As you can see from the slide, photons are split up by their wavelength. Now, if you're unfamiliar with the term wavelength, you can think of waves in the ocean and imagine the distance between the top of one wave and the top of the next. That's wavelength. So we define our electromagnetic waves from longer wavelengths, things like radios and microwave, to the very short wavelengths like X-rays and gamma rays. However, in this discussion, we're only going to be focusing on the visible spectrum. Now, in that case, let's take a closer look at the visible spectrum. Within this subsection of the spectrum is every color that we can see. From this wonderful diagram, you can see that color shifts from blue to green to red as the wavelength increases. Now, I'm going to show this really quickly. The wavelength is this value right here. So dark violets are going to be about 400 nanometers, blues are about 475, and it goes all the way up to 800 where it enters the infrared. It's important to bring up electromagnetic radiation because then we can reference an important concept for the color of our sun, and this is that of the black body. This is a concept from thermodynamics. I'd like you to picture a perfectly round sphere that's perfectly black. What's interesting about this is that if it's perfectly black, it must absorb literally all incident photons and radiation that will hit them. However, like I said before, radiation has energy, and this means that the ideal black body would eventually become extremely hot. So, to balance this out, a black body must also radiate photons outwards, and they do this at many, many wavelengths. I've included here a diagram. So I'd like you to imagine that this yellow line that you can see is a photon coming in. in our model perfectly black sphere, we're actually going to pretend that it's a solid sphere with a small hole and that this photon goes in. As you can see, it's hard for it to escape as it keeps bouncing around. And so we can think of this as being effectively captured. Until later on, eventually, it will happen to have to shoot out the same exact hole, showing that a black body must indeed radiate everything that it absorbs. This isn't a perfect analogy, but it's a very common one, and it's good enough for us right now. So now let's start talking about the color of the sun, and we're going to look at this graph. Now, it's a wildly confusing graph to look at, so I'm going to take a moment to discuss it. This type of graph is a type of graph called a histogram. In a histogram, your possible values are going to be listed along this bottom axis right here. And so if you look at this one, it starts out at 0 wavelength light, and it goes all the way up to, well, here it's listed as 3 nanometers, but a lot of times this will be a longer one. I'm sorry, this is a micrometer, isn't it? I'm not exactly sure, I can't recall. In any case, on the left axis here is the intensity. So in a histogram, what this measures is how many times we've counted seeing something of whatever value is along this bottom axis. So in the case here of this top line, the one where we're looking at a 4,000 Kelvin object, you can see that up here in the visible spectrum is where most of the photons are coming in because they have the highest intensity. So this, I will say this as well. This particular black body diagram is not of the sun. It is of a different object. I just used this as an example. So let's go over what this means for the sun. All right, I'm sorry. Let's go over what this means for different types of stars. If we look at a case of a small and cold star like the red one here on the left, you can see that the intensity follows up in this direction. It peaks outside of the visible range. So it's actually going to look like the closest thing in the visible range, which is sort of a darker red. In the case of a much larger and hotter star, it's going to be blue. And you can see over here that this intensity peaks just outside of the visible range as well. Now, you might be a little bit concerned about how the fact that this one's pink and it doesn't seem to be blue, like I kind of alluded to. But we'll talk about that in a little bit as well when we talk about why the sun doesn't match up exactly to what it looks like. Now, because we're doing this, it might seem to you like I'm taking the long way around, and you'd be right. I just want to fully justify all of this to you. And so we only have 1 or 2 more steps. So in order to look at the sun specifically, we need to use a fairly famous formula called Wien's Displacement Law. Wien's Displacement Law is right up here in the top left. It's going to be the maximum wavelength produced in one of these black body diagrams is equal to a constant B over the temperature of your object in Kelvin. So the temperature of the sun is known to be 5,800 degrees Kelvin. Sorry, Kelvin, not degrees Kelvin. And this gives us a peak wavelength of about 500 nanometers. Looking at the visible spectrum, that means that the sun is actually green. So it's kind of strange, isn't it? It's right that the sun is a very vibrant green color. Now, you're probably looking at me. I'm sorry, yeah, the sun is in fact green. Now, you're probably thinking to yourself, and you're asking yourself the same question that I first had when I encountered this. If the sun is green, why do we see this? And you've asked a wonderful, wonderful, but difficult question. And for this, I'll need to invoke color science, but I'll only do so heuristically. Our explanation for why the sun appears as it does is based on a thing called the Planckian locus. The Planckian locus is a line through a chromaticity space. Now, a chromaticity space, as an example, is actually the thing that you can see on the screen. And for this color science, we're going to have to invoke a little bit of human biology. So if you'll recall from earlier, actually, the visible spectrum, this chromaticity space ranges from about 400 nanometers around the edge, going all the way up to 500 in green, and then back down through yellow, orange, red. So in this graph, the y-axis is representative of luminance of the color as we perceive it. So things higher up here are things that we generally perceive as being brighter. And the x-axis shows an absolute value of biologically scanned responses. So now, if you recall earlier, we used Wien's law. We can actually map Wien's law as it appears along this color space for every possible temperature. Let's see what that looks like. Oh, let's see what that looks like. That is going to be this line right here. And this line is actually the Planckian locus. So as you have colder objects, they're going to, if they start to glow because of this type of radiation, they're going to start out as red, become orange, then more yellow. Then they're going to cross over here. Instead of going to green, they're going to cross over through white before heading towards blue. So chromaticity is based upon human perception of color in well-lit scenarios, as well as the thing that I forgot to mention earlier that I want to mention right now. So this is applied to things that are very bright to us. So let's take a quick look at stars now that we have an idea of what this looks like. The sun is just on the edge of human perception between yellow and white. And because of our ocular sensitivity, it appears to be a little bit more yellow rather than white when you look at it with a filter, whereas it looks just white to us from the Earth. However, hotter stars like Spica look blue, and colder ones like Arcturus and Antares are sort of a red or an orange. However, I promised you to mention some points about the relevancy. I promised you to mention some points about the relevancy of the sun being green. For this, we have to move back to chromaticity. So the left graph that I've put up here is the same chromaticity space I mentioned before. But on the right is a graph of human eye sensitivity mapped with the visual spectrum above it. And that's going to be right here. Firstly, due to the left, we actually can perceive greens as being very much more brighter, as you can see. Remember that this axis is how brightly we perceive a color to be. And if you cut this right down the middle, almost the entirety of that is going to be green and yellow. But you can see this a little bit more explicitly in the right graph. In the high, we have two peaks right here. This darker one here, or this fainter one, I should say, is actually for low light scenarios, whereas this one is for high light scenarios. So in low light scenarios, you can see that the human eye's sensitivity actually peaks almost exactly where the sun is. This is not by happenstance. But as you can see in well-lit scenarios, we start to filter out a lot of those ever-present blue photons and go towards more of a yellow one. So that means that the nature of the sun directly influences the anatomy of the human eye if you look at it through the context of the theory of evolution. However, another fun direct implication of the sun being green can be seen all throughout nature, all over the world, in any forest anywhere, and maybe even in your house or backyard. And this is in in plants. Oh, geez, my lights all slipped up. This is in plants. So the reason plants are green are actually because the sun is green. If you'll recall back to maybe high school chemistry or biology, wherever you happen to learn this, plants transform light hitting them into usable energy through a process called photosynthesis. Now, photosynthesis involves a plant using its chlorophyll A to absorb light, and then it's able to molecularly change the chlorophyll to be at a higher energy. The plant then has other processes which can allow the absorption of this light from the chlorophyll. Now, the one thing that kind of causes a little bit of a problem here is that objects appear as the color that they're reflecting. So if I have a red shirt, that means that any light that hits me is going to be absorbed except for red. So it's sort of strange that plants in this case are green. You'd think that if green's the most present color, plants would want to harvest that for energy. Well, it's actually kind of the opposite. Chlorophyll is a relatively fragile chemical. This means that if it were to absorb too many photons, it will actually degrade and break down. And so because there's so much green light compared to violet light or red light, plants reflect this abundant green light to protect themselves and so that they can harvest the more rare wavelengths. So that's a total encompassment of what color the sun actually is, why we don't see it as it is, and some implications of that here on Earth. Now, in any case, we've been talking about color and photons for a while. So we're going to take a short break for questions at this point, and then we'll reset and begin the next topic.
Hi, Corbin. Hi, everyone. So far, we have not received any questions in the chat. Maybe we'll give it 1 minute or so, and then if no questions have been asked, we'll move on to the next topic.
We'll give this a few minutes then, just in case anyone has thought of a question now that they want to post into the chat. If you happen to be watching this on your TV, your smart TV or something like that, then feel free to connect with your phone. Alternatively, you can use the chat that way very quickly, very easily. If you are on a computer, you're right there. We can talk about any questions that you have about maybe the color of the sun or the peak emittance of an object's light. I mean, they are fairly complex concepts, so we are more than able to talk about them.
I am not seeing any questions, so I think it is safe to move on to the next topic.
Okay, well, if there are no questions about the color of the sun right now, we'll move on to our next topic. If you do have any questions about the color of the sun, feel free to post them into the chat at any time, and we can either come back to them during our next question break, or again, if I happen to disconnect because of internet issues, Daniel and Ethan will be able to help you out. So, in that case, we can now talk about our next subject, solar storms. And this time, rather than having graphs and math, I have exciting photos and some videos, all of which are going to have credit to NASA. So the term solar storms refers to quite a few processes that can happen on the surface of the sun. These are going to be solar flares, coronal mass ejections, and geomagnetic storms. We'll also follow this section up with a look at the Zooniverse project and how it maps solar storms, and Ethan's going to lead us through that. Actually, you all can be an actively helpful scientist and possibly even get published if you do participate. And as one last note before we begin this section, I'm going to be saying the words solar and storms just a whole lot. So when we mentioned that the surface of the sun was 5,800 Kelvin in the previous section, I said the word photosphere. I've actually said it many times in this presentation so far. This refers to the outermost layer of the sun. Now what you're seeing here is an up close and high resolution image of the photosphere. I want to briefly describe why the surface of the sun looks like this, just to give a better description of the surface of the sun. As gas heats within the sun, it rises up and touches the photosphere, cools off, and then is pushed back down in continuous updrafts, much like this on the diagram that you can see. The gas flows up through this in a process called convection and comes back down. As you can see, these create firm borders, which actually map out to things like this in the sun. Each of these is called a convective cell. Now, on this slide, I wanted to show you that this particular layer of the sun, the photosphere, is extremely thin relative to every other internal region of the sun. It's important to define the surface of the sun like this because as the sun is a ball of gas, its corona actually extends far past the photosphere. However, this particular surface, the photosphere, is the one emitting photons and the light as we see it. Now, we can segue into our first solar storm. To segue to our first solar storm, we need to introduce a type of phenomena. This is the sunspot. These are temporary dark spots, hence the name sunspot, that appear on the surface of the sun. These can be anywhere from 10 to 100,000 miles across. If you'll look at the right image, this is what's called a naked eye sunspot, a sunspot so large that you can see them without a telescope. Admittedly, this is a zoomed in and mildly enhanced photo so that it's a little bit more clear. Sunspots have been found to increase and decrease in frequency on a cycle that flips every 11 years. This is a cycle known as the sunspot cycle. So the natural question to ask about sunspots is what causes them? Well, the sun has a very intricate and ever-changing magnetic fields within it. These fields can run in opposition to one another and prevent the convection process we just talked about a little bit ago. This means that these areas aren't getting that fresh-baked hydrogen right out of the oven to keep the surface illuminated and bright. And so you get these darker black spots that are cooling off. Still, every place on the sun, however, has particles flying around wildly, even in these darkest of spots. Electrons and whatnot are whizzing about at all sorts of crazy speeds. And particularly in these areas of twisted up magnetic fields that prevent the convection process, this can be amplified leading to our first type of solar storm, the solar flare. In the case earlier, I wanted to mention this as well. You can see a clearly defined border here. This is the photosphere, whereas everything past this is the corona that I had mentioned. In this case, this is a solar flare. Now, all of the solar storms that we're going to discuss today are somewhat interconnected. However, we can still discuss them separately. In the case of solar flares, these highly accelerated particles, like electrons that we just talked about, can magnetically interact with the sun's corona. And this causes massive bursts within it. So I have a short clip from NASA, actually, of a 2011 solar flare. Let's take a look at this. It's just shockingly massive considering the scale of the sun. So really thinking about it, let's take one more look back at it. It bursts out and falls back down. Visible solar flares have an energy on the scale of 10 to the 20th joules. Don't worry about the unit, I'll contextualize it in just a minute. While major events, as opposed to just visible ones, can go all the way up to being 10 to 25 joules. So to contextualize the unit of the joule, the US military produced things called atom bombs, which you may or may not be familiar with. These have energy yields of 10 to the 13th joules. An atom bomb, as such, is 1/10,000,000th the energy yield of just a regular visible solar flare, not even close to the one that we saw in this video. Now, on to the next solar storm. Solar flares are related, although the exact nature of this relationship isn't well understood, with a very similar event. This is called a coronal mass ejection. Well, when these events are large, being coronal mass ejections or solar flares, they're almost always accompanied by one another, and vice versa. However, while potentially looking similar in terms of things just flying off of the sun, they are distinct. I'm going to borrow the words of Holly Zell, an author at NASA. A solar flare is much like a muzzle flash, while a coronal mass ejection is more like a cannonball. This is to say that a solar flare is like a pop of light and energy, which then cascades back down to the sun. You just saw that in the video. It kind of like popped up like an umbrella and fell back down. On the other hand, a coronal mass ejection takes a clump of sun stuff, which is the technical term, and it flings this sun stuff outwards into space. Just like before, I have some wonderful footage that we'll look over in a second. One thing that's important about coronal mass ejections, though, is that before we talked about how sunspots have to deal with the formation of really twisted magnetic fields, this process carries up all the way through a coronal mass ejection. And so let's watch this clip. Now, I'm going to play it a few times just because it's a very short clip. And I will say, just like the solar flare and this clip, both of these are massively, massively sped up. These processes take a very long time. But in the notion of the twisting magnetic fields, you can actually see, oh, I'm sorry, I accidentally slipped ahead of a slide. Let's try to go back. You can actually see right around here, you can see it start to twist in on itself. Now, the thing that is interesting here is that you can see a lot of this does come back down, but parts of it just go on forever. Now, this next video is a little bit longer, luckily, and it's going to show, it's a series of coronal mass ejections instead. This took place in, this is the wrong one. There we go. This took place in August 2010, and you can see them popping off all over the surface of the sun, primarily on the left half. At their least frequent, coronal mass ejections will occur about once every 5 days. And at their most frequent, they'll appear up to 3.5 times a day. I'm going to play this again one more time for you. Both coronal mass ejections and solar flares are events that can start up a certain thing called a solar wind. And a solar wind is important for the last type of solar storm that we'll talk about. Now, a solar wind is going to look something like this artist's conception. Whenever a large clump of particles is jettisoned from the sun, this is called a solar wind. So pretty much all CMEs or coronal mass ejections have one. This wind is primarily made up of electrons, protons, and other small particles. However, it can catch and send out heavier elements like carbon, and even up to iron. But these things exist only in trace amounts. This wind will typically continue onwards and out of the solar system for the most part. However, as shown in this diagram, it can hit planets. An example of this very strong solar winds have been known to hit the Earth, producing a certain effect. And that effect looks a little bit something like this. And this is called an aurora. It's a closely related event is the next one we'll mention. It's something called a geomagnetic storm. This is a little bit more of an explicit look at this. In the process of solar winds bombarding Earth, oftentimes the Earth's magnetic field can be disturbed. So in this case, if you are familiar with them, magnetic fields typically go from a south pole up and around and come back down to North Pole. As you can see from these magnetic fields from the sun bombarding our Earth and our Earth's wonderful magnetic field shielding us, they get bent off, heavily contorted. And yeah, in this artist rendition, you can see this clearly because of the asymmetrical nature of it. So just like the two solar storms we've already talked about, how often this type of event occurs also matches up with how frequent sunspots are. I'm sorry, I got a message from one of my fellow presenters and it caught my attention. I'm sorry. So these talk about how often these occur at the same frequency as sunspots. Geomagnetic storms may not be as flashy in terms of imagery as coronal mass ejections or solar flares. Well, except of course when they produce aurora like this. But I do have some interesting, specific historical examples to talk about. Oh, I just lost my train of thought. I'm so sorry. I'm sorry. The first case that I want to talk about is the smaller but second largest one ever recorded. And this is in March 1989. This storm was heavy enough that it disturbed the electrical network of most of, if not all of Quebec. And it also cast aurora, much like these, all the way down to Texas. That's really, really impressive since these are typically localized to the poles of the Earth. But let's talk about the main event, the largest ever recorded event, the Carrington event. This took place the first 2 days of September 1859. This was just following the construction of the United States telegram system. This storm was so massive that it overloaded and destroyed major portions of this network. Additionally, it even electrocuted several operators of the telegram system and started many fires. All in all, the surface of the sun is a much more active beast than we often perceive it to be. It's always shifting and churning, and it throws hunks of itself off into deep space, and it shifts on an 11-year cycle because of the magnetic fields. Now, before Ethan's going to take over talking about the Zooniverse project and how it relates to solar storms, I'm going to have Daniel open up to convey your questions to us.
Hi, everyone. So we have a couple of questions in the chat. The first one I'd like to ask here is Freedaz3 asked, how large is a typical solar flare?
How large is a solar flare?
And could it be measured in miles, and how dangerous could they be to the planet?
So solar flares potentially are dangerous to the planet. They're actually one of the things that were concerned. There was a lot of concern about them, if I recall, about a decade ago, in that they are just bursts of electricity and magnetism, and they can disrupt this. However, those are going to be the extremely large cases. In terms of how physically large they are, I'm actually not certain of this one. Ethan, Daniel, do either of you happen to know?
I do have an answer to this one. They are fairly large, at least about roughly, I think a typical is 10 or so diameters of Earth, which is just massive. So
large. Okay, you
yeah,
said we have a few questions. So
we have a few questions. So another question is it possible to have solar lightning? This is a question from Caleb Medchill.
Solar lightning is, well, I guess in theory it's possible, but in the case of thinking about like a cloud shooting a lightning bolt down to the earth, this is not a thing. Solar storms do not produce clouds, as the atmosphere of the sun works a little bit differently here.
Okay, another one from Jen Gisler. Why do sunspot cycles happen every year?
I believe Ethan actually knows the answer to this one and have been planning it out.
Yeah, so the question is a little complicated because the sun does not have what one would consider a typical magnetic field like the planets. The planets have a very well-defined, very stable magnetic field, but due to the complicated physics behind the sun and how all of the various high temperature and high energy molecules and everything interact with each other, the sun's magnetic field is a very, very messy thing. Um, but it actually does have cycles, and one of those cycles is that it flips its polarity every 11 years, and as such, everything kind of everything starts out, I guess the best way to call it is small. So, sunspots typically start out very small, very minor, and then as the 11-year cycle goes on, sunspots typically get much larger, much more frequent. Um, And then this comes to a head every 11 years, at which point the complicated interactions of the magnetic field cause everything to flip polarity completely and go all the way back down to square one and start all the way over from there.
If you're looking for a slightly more in-depth description, this process is typically called magnetic. It's the sun in a natural state has a magnetic field much like the Earth. You can imagine the Earth as having kind of like a classical long magnet with a north pole on one side and a south pole on the other side going through the middle of it. The sun has something similar, but since the sun isn't solid, this can kind of twist, and it eventually twists into this very long, complicated spiral. And this process takes about 11 years. It becomes so twisted, in fact, that a process that we won't be discussing in further depth here called magnetic recombination happens, wherein the more or less nature just doesn't like dealing with this complicated spiral, and so it just straightens it out and flips it. And this process actually is what causes solar flares and particle acceleration within sunspots on a smaller scale throughout the convection cells. Daniel, do you have any other questions in the chat?
Yes, we do. So
Fantastic.
These next two questions, they're similar, so we can link them together. Emily D asks, how long does this process solar flares usually take? And Caleb Medchill asked, why do solar flares take so long? Wouldn't they be taking place at the speed of light? Now, I do have the answer to the solar flare. The process takes usually about an hour. They can last several hours, but it's usually on the shorter end. And
I believe solar flares typically are something around like 10 to 30 minutes long is the whole process, right? Something
I think I think a little longer, but around, yeah. And to answer the other question, I think I don't know this one for certain, but I would imagine that it isn't going to take isn't going to travel at the speed of light, or process isn't going to happen at the speed of light, because the sun is ejecting material, and that material can't travel at the speed of light. We can see it, the light that it emits can travel at the speed of light, but I think that the material that's being ejected is going to be slower.
Yeah, to use a little bit of a higher concept terminology, the material is typically in solar flares and in coronal mass ejections, it does become accelerated to relativistic or near the speed of light speeds. However, this isn't going to say that we're at 95% of the speed of light. This is going to be something like 30-20% of the speed of light at most. And immediately upon leaving the heavily accelerating magnetic fields, things do not like to move that. Matter doesn't like to move that fast, and so it immediately starts to slow down and pour back down to the sun.
It's also important to keep in mind that these are very large scales. It may look like small relative to the size of the sun, but it's also important to realize the sun is massive.
The sun is large.
Mm-hmm.
Yes.
And one last question, which is kind of a segue into our next topic, or to the activity. Peace 2051 asks, are researchers using AI to analyze the filament patterns of the sun's surface to mechanisms that cause it. I believe that this is going to segue into the next topic because they the primary use right now for analyzing the surface of the sun is with citizen scientists, and that's our topic next, or our activity.
Yeah, so actually, one last question came in, so I'll bring it up here. Jen Listener asked, has any material ejected from the sun reached the Earth? That is a definite yes. Any aurora that you've ever watched in your life is material from the sun interacting with the Earth's magnetic field. So, uh, the exact size and how intense the aurora is dependent on how energetic and how much material hit the Earth at that point in time. And then to go back to Pisa's question, this is actually an excellent segue into our little activity today. So, yes, AI is a big part of sort of figuring out the sort of stuff about the sun's surface and coronal mass ejections and all the other various solar storms. But on top of that, there's also citizen science projects. The particular one we're going to be messing with today is called the Zooniverse Project. The Zooniverse Project is a collaborative effort between professional scientific research groups and citizen science groups who are helping the professional groups do a lot of the research that the scientists themselves might not have time to do. So kind of the goal with this particular project, which is called Protect Our Planet from Solar Storms, is to take a look at images of various solar storms to see if the citizen scientists can pinpoint reoccurring patterns and sort of general structures that professional scientists might be able to take a look at and say, okay, if this is happening, then this is a sign of whatever size storm. Um, and that's really important to us because if we're able to determine how large and how energetic a storm can be, that can help us to prepare for situations where the storm might be strong enough to bypass the Earth's magnetic field and damage either our infrastructure or even the planet itself if we happen to have a particularly extreme situation. So this activity comprises of two different scientific sort of goals. The first one is to compare the complexity of different solar storms. So Zooniverse has a full written out tutorial. If you want to get the full information, make sure to read through that. I'm just going to be kind of quickly breezing over it so we can discuss both of the projects here. So the goal of this particular one is to look at the left and right image and determine which of the two is the more complex of the two, like I said. The simpler solar storms are going to be ones that have a very well-defined structure. They're probably going to be a little bit smaller. And in general, it's going to be very easy to pinpoint, okay, this is what this looks like, and it has, these couple, 3, 4 well-defined structures in it. Whereas a more complex solar storm is going to be one where it's typically much larger, much more dispersed. It's going to look a little more like the one on the right, actually. Very messy, very undefined sort of a thing. So with this one, we would choose the one on the right because that's the more complicated of the two. And then you would go from there. So that is our first activity. And the second one is the Draw a Storm Front. Once again, this has a full-blown tutorial. I recommend you read through it if you want the full details. But to just quickly breeze through it, instead of picking between two images, you're going to instead take a look at a single image and try to outline the general shape of the visible solar storm. So in this case, we would draw something, a little something like this, and then submit that. And by doing this and by having hundreds upon thousands of people doing this, this helps scientists to really get a well-defined image of these solar storms and get a very good detailed description of like how complex is it, how large is it, and whatnot. And by having all these different people looking at these same collection of images, we reduce a lot of the potential error that might have come from, say, 3 or 4 scientists only looking at it. So that is just those two. We're going to give you guys 3-4 minutes here to just kind of play around with them. If you have any questions about it, feel free to post in the chat. I'll answer them as best I can. And then after we give you guys a little time to work with it, we're going to be talking about what Zooniverse actually does with this information after the citizen scientists put it together here. Oh, I see. So while you guys are working with this, I see Jen Glistener has another question. Assuming larger suns in other systems behave the same way, can you measure their aurora?
So the question is on interstellar aurora and if we can perceive them. So if we assume that planets form in other stellar systems, much like our own, such that they have magnetic fields, they should, in theory, also have aurora. Other stars, I believe, have been. I can't explicitly say this, but I believe that there have been cases of solar flares on other stars that have been able to be observed. And since solar flares sort of imply coronal mass ejections and they imply geomagnetic winds, and so as long as other planets in other stellar systems have their own magnetic fields, there should be aurora. However, to us here, that's too small of a scale for it to be visible.
I was actually talking about this with Corbin and Ethan earlier. We were discussing whether or not we think other planets in our solar system also experience auroras, and it was kind of exciting to discuss the topic. Do either of you guys want to input on that topic?
Yeah, so we actually found that anytime that there is a relevant enough magnetic field of a planet, it will have auroras, although they do look slightly different. One of the cases is if you, I don't have a slide for this one, so you'd have to look this up on your own phone or something like that. But Jupiter actually has a fairly luminous blue aurora. They're really interesting, and they're so unlike on the Earth, which they can kind of spread the whole way, since Jupiter is so large, they're very localized to the poles. I believe that certain other planets in the solar system also can do this, but I haven't seen it. I didn't look into any cases besides that of Jupiter.
I believe all of the gas giants have a similar general effect. However, actually, Earth is the only rocky planet that can have auroras. Mercury obviously doesn't really have its own magnetic field. Venus also actually doesn't have its own magnetic field. It instead uses its ionosphere to protect itself from solar winds. And it is believed that Mars once had a magnetic field, but due to its relative small size compared to something like the Earth, it lost its ability to generate a magnetic field and therefore lost its protection against solar winds, which is also why Mars does not currently have much of an atmosphere to speak of.
All right, and then just to give it an extra minute here, just in case anyone still wants to play around with the, I shouldn't say play around because it's serious science, and in case anyone wants to still use the Zooniverse project. Okay, and I just have to set up my slides again and make sure that I'll be the one presenting here as we just switch back over.
Okay. While Corbin's doing that, I just want to go over, like I said, I just want to show you guys excuse me. I would just want to show you guys what Zooniverse is actually doing with this information that you guys are generating right now. So if you take a look at the project's main page, you can see a little project statistics on the middle of the page here. You can see that 33% of the total project images have been categorized, and you can see the number of volunteers, how many classifications have been done, and all sorts of general information like that. So you can see there is a very large amount of information that has been generated from this project already. And if you want to go into real deep detail on like what's being done, you can go into the Learn More tab and you can see the actual research itself, like specifically that's being done. You can learn about the professional science team that is heading the project itself, and you can actually see a lot of the results that have been generated from just the citizen scientists alone. And actually, a lot of this information has and will be published in actual scientific literature. So like we said at the very beginning, if you guys commit, or if you guys work with this project a lot, you yourself can actually be credited in the publishment once the data gets sent out. So this is actual real research that you guys can participate in just by clicking a few things on your screen. So, and then if you guys want to see the publications, down at the very bottom, there is a publications tab. It has most of Zooniverse projects, not just the solar related ones, but if you look around enough, you can find the solar ones, and you can look around and see what other sorts of projects that Zooniverse is also currently working on. But that being said, I will hand it back over to Corbin.
All right. We might have a technical problem here. Are we back to the question slide, Daniel?
We are.
We are. Fantastic. Okay. Well, in that case, finally, we've come to our last discussion piece, the past and future of our sun. So we're going to talk first about how the sun formed, what its stages will be like while it's still in its main process as it is right now, and finally how it will die and leave behind what it will leave behind. So we'll begin with a stellar nebula. These are very dense clouds of gas in space, formed due to gravity pulling many dust particles together. These can also be called stellar nurseries or Bok globules. Now, unlike earlier when I was joking about technical term being sun stuff, this is the actual technical term, is a Bok globule. Try to say that. I practiced a lot. But anyways, on this slide that I've shown you right now is the Rosette Nebula. This is a very large wide-angle photo, but you can still see the clumping of dust that's going to be happening right in here and right in over here. So this whole nebula, all of this that you can see is dust, and as time passes, gravity pulls it together into these big things. Now, the Rosette Nebula is rather beautiful, but we're going to look at a slightly closer nebula so we can see it a little bit better. This is going to be the Elephant's Trunk Nebula. Now, I have two different composites here posted. One of them is in the classic Hubble composite over here. This one, I believe, was actually taken by Hubble. I don't recall which telescope took this one. I think it was the Spitzer Space Telescope. I could be wrong. That could be a different one that I've seen. But in any case, you can tell that these are very dense clouds of gas. I'd like you to look over here on the left one. You can see the background stars are very numerous and ever present. However, within the fields of the gas, like here or all along up here, it's completely clouded out. However, along this purported trunk, you can see several twinkling spots. These are young stars and protostars, but we'll get more to what the word protostar means in a minute. So out of these diffuse and sparse clouds, in time, they'll clump up and they'll clump up into these sorts of shapes that are as gravity does its work. But like I promised, it doesn't stop there. As these clumps continue to build up, all the while hydrogen and other particles are just bumping into one another. The space for these tiny elements gets smaller and smaller, and they start to bounce against each other more quickly and quickly and quickly, and then they heat up. They eventually get hot enough to glow. You can think of this as being like the filament of a light bulb. And once this happens, we have a protostar. The one I have pictured here is HBC1. So now we've had cosmic dust coalesce down into a ball. What's more is that ball is so hot that it glows. This is where we can really begin to marvel at the process of gravity. As this ball has formed, it now has so much more material than all of the surrounding space that it becomes a gravitational well. That means that a lot of the same process that has been happening is going to continue to happen. The protostar is going to continually pull in more and more matter as it sucks it out of nearby space. And as the protostar continually pulls in more matter, it gets more dense and thus more hot and more bright. And you'll recall earlier when we talked about the color of the sun that high temperature means it radiates energy. This process of radiating energy allows the budding star to contract and shrink, tightening the material even more. These processes of gravity attracting material and gas contracting continue until one exact moment. And that's when two hydrogen atoms become so energized that they're able to fuse into helium. With that action, any star
It appears Corbin's internet might be having some issues, unfortunately. Oop. Yeah, it's probably going to take him a minute to get back. In the meantime, if anybody has any questions about what's been discussed so far, feel free to post them in the chat.
my back on.
It seems like you are.
I was hoping that it wouldn't happen, but this is why we took the case in the beginning. Could one of you two please tell me where I had left off when I got severed?
Protostar ignition.
Fantastic. Yes. So the action of two hydrogen atoms fusing for the very first time into helium is how our sun was born in the process called protostar ignition. Now, this right there, following protostar ignition, is the current stage of our sun. In this part of a star's lifespan, it lives on something called the main sequence of stars. This is something we can clearly define with an HR diagram. So as you can see here, ignore these for now, and these for now. We'll come back to them, I promise. This diagonal right here is the main sequence. It relates the brightness or luminosity of a star from low to high with its temperature. Now this one's a little bit backwards. It goes from high temperature to low temperature. Our sun is right here on the diagram. However, even though it's this main sequence star, it doesn't remain constant and stable. Well, it remains stable, but it doesn't remain exactly constant. The heat and energy in the focus of our solar system comes from the atomic process of fusion that I just mentioned. This process gives off enough energy to keep the sun stable. So as gravity is trying to pull together all of this material that's swirling around, the core is letting off energy in sort of a constant explosion that's fighting back against gravity. And this creates a hydrostatic equilibrium, to use big words. However, very slowly, as two atoms are converted into a single atom, piece by piece, the sun shrinks slightly. This is because once the amount of hydrogen in the core will decrease. As it decreases, the energy output of the core will also go down because less fuel is available. Gravity will then start to set in and contract the sun, leading to it shrinking and contracting over time. This indirectly means that the sun is always slightly contracting, getting a tiny, tiny bit smaller as time passes. Now, hopefully this seems similar to what we talked about earlier with the protostar. However, in this case, this process takes roughly 10 billion years. Eventually, the sun, because of this process, the sun will become small enough such that its core will become hot enough to fuse helium into something that changes the sun. And this process of the initial burst of helium fusion is a helium flash. And with this flash, it will shift into a red giant. Helium fusion is much, much more energetic than hydrogen fusion. And so because it can fight back stronger against gravity, the sun will balloon up. So large, in fact, that it will consume the Earth's orbit, as you can see in this diagram. If you recall from earlier, these actually do appear on the main sequence. We had them. They don't appear on the main sequence. They appear on the HR diagram. I'm sorry, I misspoke. Those are up here. These are the giants and supergiants. Supergiants are related more to very large stars as opposed to just red giants, which is what our sun will become. Now, let's take a cross-sectional look at a red giant. Between our main sequence sun and a red giant sun, the difference is rather subtle. In the main sequence, we're going to fuse hydrogen and deposit them into an inert helium core, while the red giant will fuse helium into a new inert core of carbon and also beryllium. This process is a little bit more complicated, and so we're just going to skip over that one today. Now, again, because of this, eventually the helium will start to run out, and the sun will contract again. However, while larger stars can continue on in this path of contracting and getting bigger and contracting and getting bigger, this right here with a carbon core is where the sun will call it quits. The following process of fusing carbon is so energetic that our suns won't actually be able to handle it. The sun isn't massive enough to hold itself together with gravity as the carbon fusion blows itself apart. This process of the sun blowing itself apart will form a planetary nebula. I have two photos of this. One on the left is a younger planetary nebula. It's the lemon-sized nebula, and the one on the right is a little bit more famous one, and it's a little bit older, the Ring Nebula. In the bursting process, the outer layers of the sun will be thrown out in a massive solar wind. This process will leave behind a small, dense, and hot core that you can see in both this image here and in this image here. This core is called a white dwarf. White dwarfs are on the scale of the size of the Earth. However, they still have the mass of an entire sun, or larger or smaller star. This is the end of the evolution of our sun. Fusion no longer takes place in white dwarfs, and so they can simply be thought of as very, very bright rocks. Our sun's white dwarf will be made up primarily of carbon and oxygen, as that's going to be what happened. That's going to be the final fusion process that takes place in the core. Now, let's take one last look at the HR diagram, and you can see that white dwarfs do in fact live down here on the HR diagram. They're very, very hot, but they're very, very dim. Now, because these things are so hot, we're going to bring it back one more time to the black body. They do let off their heat through thermal radiation. Eventually, white dwarfs will cool down, but this cooling process is so projected to take so long that it actually oftentimes is longer than the age of the universe. And so the cold remnant of one of these, a black dwarf, is at this time an entirely theoretical object. However, given enough time, it is likely what our sun will amount to. And as we close the book on our sun's life, we will open up to questions.
Hi, Corbin. Hi, everyone. There was one question in the chat, and if anybody has any more, feel free to ask. There was one question from Caleb Medchill. He asked, does the sun and age correlate to solar flare size? I know a little bit about this one, but does anybody else want to discuss first?
I'll let you take this question, Dan.
So I didn't initially know the answer, but it looks like solar flares depend a little bit on the temperature. So to me, that signifies that if it depends on the temperature, bigger stars and younger stars tend to be hotter. So I would imagine that the flares are probably larger or more intense for younger stars at the very least. And younger stars, as Corbin has mentioned, tend to be hotter. Is that yes?
That is correct.
Sorry,
yes.
younger stars do tend to be hotter
Yeah.
because they have a more active core, yes.
Mm-hmm. And I also found that also allows for a type of phenomenon called a super flare, which are about 10,000 times the size of a normal flare. And these super flares tend to happen, again, in younger stars. I believe they found them in stars about our size, but they're about our age, but they're typically younger stars. And I do not see any other questions in the chat as of now, so we'll give it a couple minutes in case anyone has any further questions. And if not, then everyone can have a fantastic day.
Yeah, at this point, thank you for coming to Universe at Home and talking about what goes bump in the day with us. We're all glad to help you or to talk to you all here. Next week, if you do, I'm sorry, not next week, 2 weeks from now, as you come back on October 21st, the presentation will be Starlink Stealing the Stars, if you're interested in that one. But like Daniel said, you can feel free to close out now as the talk has been completed, but we will still be taking questions for a few more minutes.
And make sure to check out the Zooniverse project, even if you're not interested in the specific solar project we took a look at. Zooniverse has hundreds, if not thousands, of other possible projects you could take a look at, from things like average algae sizes to obviously solar storms. So any project you assist with is only helping science further its knowledge. So any help in any project you decide to work on is always very welcome.
We do have one more question from Caleb. He is asking, would the angular velocity of the star affect the size of the solar flare the same as the way temperature does? Does anyone have an answer to this one?
I believe, yes. So I believe, and I'm going to invoke a little bit of the deeper concepts here as we talk about this. The magnetic fields get all twisted up as we talked about. And these twisted up magnetic fields pile up towards the center of the sun or any given star. And so in the case of a star of the sun, these are more frequent towards the what am I trying to say here? The equator. I think that term is applicable towards the equator of it, because that's where these magnetic fields pile up. And this is actually the reason that they contort and twist, is because the angular velocity of the sun changes as you go from one of the poles to the center, because it's a fluid.
There is also, upon the research of the super flare, they do mention that it can't be a rapidly rotating body, and I think that makes sense, as if it's rotating too quickly, I believe it's called quenching the activity that solar flares. So I believe it needs to be, not super fast, and so I would imagine it definitely has a dependence on the angular velocity. That seems to be the last question.
Caleb's got one more question for us here.
Oh,
Would that mean if there was an outside magnetic field, the solar flares could be stopped? That is correct, actually. As we showed with the Earth's magnetic field, external magnetic fields are capable of stopping solar flares, and as a result, creates things like the auroras that all of the planets with magnetic fields experience during particularly extreme solar storms.
All right, Daniel, do we have any other questions at all?
It does not appear to not appear to be any other questions.
In that case, thank you all so much for coming tonight, and have a wonderful rest of your day.